and non-ideal solutions. Coming to the next part of the chapter, we are talking about ideal and non-ideal solutions. What are they? Liquid solutions can be classified into ideal and non-ideal solutions on the basis of Raoult's law. So we saw the Raoult's law, and it's another form where solutions had a non-volatile solute also, right? Now coming to ideal solutions, the solutions which obey Raoult's law over the entire range of concentration are known as ideal solution. The ideal solutions have two other important properties. The enthalpy of mixing of the pure components to form the solution is zero, and the volume of mixing is also zero. That is, there is no energy exchange when there is no enthalpy change when the mixing of the pure components take place, as well as there is no change in the volume when the mixing of the components takes place. That is, delta H mix is equal to 0 and delta V mix is also equal to 0. It means that no heat is absorbed or evolved when the components are mixed. That is, there is no energy exchange. Also, the volume of solution would be equal to the sum of volumes of the two components. That is, before the mixture, that is volume of the pure components summing up would be equal to the volume of the solution also, right? And at molecular level, ideal behavior of the solutions can be explained by considering two components A and B. In pure components, the intermolecular attractive interactions will be of types AA, BB, whereas in the binary solutions, in addition to these two interactions, AB type of interactions will also be present, because when there is a mixture, now AA interaction also will be there, AB also will be there, and BB also will be there. That is what happens when there is a formation of solution, right? The intermolecular attractive forces between AA and BB are nearly equal to those between AB. This leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Now they have given examples also. So summarizing, let me give you 5 to 6 points about the ideal solution. So first point would be the solution would obey Raoult's law over the entire range. That is your ideal solution. Second point would be they have two important properties, that is delta H mix also will be equal to 0 and delta V mix also will be equal to 0. Now explaining this second point, you have to say that delta H mix is 0, that is enthalpy. There is no change in enthalpy, that is there is no heat observed or evolved when the components are mixed, and delta V mix is 0, that means there is no change in the volume before the dissolution and after the dissolution. That is, the pure components volume will be equal to the volume of the solution. Now the third point would be at molecular level. First we saw what is ideal solution. We stated that solutions following Raoult's law are ideal solution. Then we stated the properties of two important properties of ideal solution through which you can find out that this is an ideal solution. Delta H mix will be equal to 0 and delta V mix will be equal to 0. You need to explain what is delta H mix equal to 0 mean, right? It means that there is no heat is absorbed or evolved, and delta V mix means volume will be equal. Now this will be your second point. Third point, you have to state about the molecular at the molecular level, ideal behavior can be explained through. So at the molecular level, let us take component A and B in the solution that we are going to, ideal solution that we are going to prepare now. Okay, so in pure components, that is pure components, component A. In the component A, the intermolecular attractive interactions would be among themselves, right? AA interaction only will be there in the component A, and similarly for component B, BB interaction will be there. But in the binary solution, adding the two components A and B, there will be another type of interaction, that is AB type of interaction. There will be AA interaction, AB interaction, BB interaction also. Now, if the intermolecular attractive forces between AA and BB separately in their pure components equal the AB interaction in the binary solution, then they are ideal solution. That is, the intermolecular attractive forces between AA and BB are nearly equal to those between AB after the formation of the binary solution. Then this will lead to the formation of ideal solution. Now a perfectly ideal solution cannot exist, but some few examples provided here are nearly ideal in behavior. So examples, and okay, let me tell you that after going through non-ideal solutions also. So solution of N-hexane and N-heptane Bromoethane, chloroethane, benzene, toluene, etc. fall into this category. So remembering the example for ideal solution is very simple. N-hexane, N-heptane, bromoethane and chloroethane. Remembering two of them will be wo kafi hai, right? Then non-ideal solutions. Now when all opposites of ideal solution will be stated in non-ideal solution, that is basically the solution won't obey Rolle's law over the entire range. Then the vapor pressure of such a solution is either higher or lower than that predicted by Rolle's law. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Raoult's law. The plots of vapor pressure as a function of mole fraction for such solutions are given in the figure 1.6. We'll come to the figure 1.6 little later. The cause for these deviations lie in the nature of interactions at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker than those between AA and BB. That is, in this case, the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute-solute and solvent-solvent molecules. This means that in such solutions, molecules of A or B will find it easier to escape than in pure state. This will increase the vapor pressure and result in positive deviation. Now, to not worry that I've been reading the paragraph as it is, I will explain. So, when a solution does not obey Rolle's law, this was the first point in ideal solution, that it will obey Rolle's law. So, non-ideal solution, write the opposite of it, that is, a solution will not obey the Rolle's law over the entire range of concentration. Then, in such solutions, we have seen this Rolle's law formula, right? Using Rolle's law's equation, you would be finding the vapor pressure, right? That vapor pressure will not be the same for non-ideal solutions in the actual case. That is, the vapor pressure of such a solution will be either higher or lower than the predicted vapor pressure by the Rolle's law equation. You would be getting a value when you use this equation, and you will be getting a value when you do it experimentally. So when the values mismatch, then they are known as non-ideal solution. That is why they say that the solution do not obey Rolle's law, because the vapor pressure of such a solution is either higher or lower than the predicted Rolle's law predicted by the Rolle's law equation. Now if it is higher, if the vapor pressure found experimentally is higher than that predicted by Rolle's law, listen carefully, if it is higher than that predicted by Rolle's law, then it is positive deviation. That is, the deviation caused is positive. That is, the deviation created is greater. That is, the vapor pressure has become more than expected. Then it is positive deviation. If the vapor pressure is lesser than expected from the Rolle's law, then it is negative deviation. Now the plots are given below, that we will see later. Now, coming to the molecular level, see, for positive deviation, we saw that the vapor pressure will be higher. That means the interactions at the molecular level, the interaction of AB would be weaker than those in AA and BB. That is, in the pure component, solute-solute or the solvent-solvent interaction would be stronger than the solute-solvent interaction. Now, when the solute-solvent interactions are weaker, then that means the solute or the solvent, when they are volatile, can escape easily into vapor phase. When the molecules can escape easily, then we easily know that the vapor pressure would increase. So this will increase the vapor pressure and result in positive deviation. That is why in the positive deviation there is an increase in the vapor pressure than expected, because of the intermolecular attraction between the solute solvent molecules being weaker than that present in the pure component. Now, mixtures of ethanol and acetone behave in this manner. So, ethanol and acetone mixture is the example for positive deviation. Remember carefully, examples of ideal and non-ideal solutions are very, very important. Again, these are one markers. There are frequently asked questions that state the examples, give examples for ideal solution, give examples for positive deviation, give example for negative deviation. So, try to remember the examples very carefully. Okay. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecules and break some of the hydrogen bonds between them. Due to weakening of the interaction, the solution shows positive deviation from Rolle's law. So, they have given in figures 1.6a. So this is a graph between vapor pressure and mole fraction. Now chi1 is the mole fraction of your solvent, and chi2 is the mole fraction of your solute. So the mole fraction of solvent increases from 0 to 1 this way, and your chi2 decreases from 1 to 0, or maybe it increases this way. So the vapor pressure expected from Rolls Royce is given in this dotted green line, right? So the expected vapor pressure of P1, that is your solvent, was this, but due to the mixture it got deviated into this blue curve. Again, the expected vapor pressure from P2 was this, but due to the alteration in the vapor pressure after the formation of solution, it got this blue curve, and your P total will be this curve. Now this is a positive deviation, so all the curves are facing upward, like they are upward facing, right? Now, in a solution formed by adding carbon disulfide to acetone, the dipolar interactions between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. This solution also shows positive deviation. Again, they are giving another example. So, for positive deviation, the examples would be ethanol and acetone, or carbon disulfide and acetone. See, the acetone part is remaining same. So, for positive deviation, examples would be ethanol and acetone and carbon disulfide. For both of them, the solute solvent interaction between the solute solvent molecules are weaker than those in the present in the pure component. So there is a positive deviation in the you know there is a positive deviation in the Rolls Royce, and this is a non-ideal solution. In case of negative deviation, what will happen? There will be a decrease in the vapor pressure than expected. This is because in the intermolecular attractive forces between AA and BB are weaker than those between AB. That is, the binary solution formed would have a stronger solute solvent bond than it was earlier in the pure component, leading to decrease in vapor pressure resulting in negative deviation. Now when the binary solution contains a stronger bond, then the chances of the component's solute or solvent escaping to become, to form the vapor and creating vapor pressure would be less, right? The number of molecules escaping would be lesser than that compared to the earlier stage. So there will be a decrease in the vapor pressure resulting in the negative deviation. An example of this type would be phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule as shown. This decreases the escaping tendency of molecules for each component, and consequently the vapor pressure decreases, resulting in negative deviation from Raoult's law. So we had seen ideal solution. I told you 5 points for ideal solution. Actually I told you into 3. You can make it as 5. First one is nothing but they obey Rolls law is the first point. Second point would be delta H mix is 0 and delta V mix is 0, and the third point would be explaining what is delta H mix 0 and delta V mix being 0. Then the fourth point would be at molecular level you can say that AA-BB interaction would be equal to AB interaction. That is nothing but both the molecular interactions are similar. If the component interaction is similar, then that will form your ideal solution. And your fifth point would be that you will say the examples. It is N-hexane and N-heptane, mixture of N-hexane and N-heptane, mixture of bromoethane and chloroethane, and if you want you can also say benzene and toluene. Now coming to non-ideal solution, we saw that it won't follow Rolls law, and there are two types in this non-ideal solution. One is positive deviation from Rolls law, and the other one is negative deviation. We also saw what is positive deviation. Positive deviation is there is an increase in the vapor pressure. This is because the molecular attraction that was created after the formation of the solution would be weaker than it was priorly in the pure component. So when the attraction is weaker, escaping tendency, like the easier it is to escape, and there will be increase in the vapor pressure. That is why it is positive deviation. The negative deviation is nothing but lowering of the vapor pressure. That is because the formed binary solution would have a greater interaction. That is, the molecules would have a stronger interaction than that present in the pure component, and so there will be a decrease in the vapor pressure because the amount of molecules that can escape in the solution would be lesser. So there, they have also given the examples for positive deviation. For positive deviation, ethanol and acetone, or what is it is carbon disulfide and acetone. Now coming to negative deviation, the examples would be chloroform acetone. So they have stated why, because chloroform molecule is able to form hydrogen bond with acetone molecule, and we know that hydrogen bond is very strong. So the solute solvent bond is stronger here, therefore the escaping tendency of the molecules decrease. That is, the escaping tendency of the molecules for each component decrease, and so the vapor pressure decreases, resulting in negative deviation from Rolls-Royce. And another example for negative deviation would be your phenol and aniline. Again, the same reason. In this case, the intermolecular hydrogen bonding between phenolic proton and the lone pair of nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding. Therefore, the solute solvent bond here is stronger than the solute solute or solvent solvent bonding. Therefore, the escaping tendency, again the same thing, it decreases the escaping tendency of molecules for each component, and the vapor pressure also decreases because the number of molecules escaping from the surface of the solvent, from the surface of the solution is lesser. Therefore, there will be lesser molecules converted into the vapor phase, and those molecules exerting pressure on the solution itself above the solution will be lesser, because the pressure exerted will be lesser because the number of molecules are also lesser. Therefore, this results in decrease in vapor pressure. Now, some liquids on mixing form azeotropes, which are binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. Before coming to what they are, let me tell you that azeotropes definition is very important here. They might ask, what are azeotropes? So they're nothing but they are binary mixtures, in the sense they are mixtures containing two components having the same composition in liquid and vapor phase and boil at a constant temperature. Azeotropes are binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. So when they can boil at the constant temperature and they have same composition in liquid and vapor phase, then it is difficult to, it is not possible to separate the components by fractional distillation. When they have a minor change in their boiling point, then only they can be separated by where the first component would escape in the minimum boiling point and the other one would stay in the distillation container, right? But here, when they can boil at the constant temperature and they have same composition in liquid and vapor phase, then they cannot be separated by fractional distillation. Now, the two types of azeotropes are minimum boiling azeotrope and maximum boiling azeotrope. What they are is that the solutions which show a large positive deviation. So we saw that solutions show positive deviation and negative deviation. When the positive deviation is very large, then they form the minimum boiling azeotrope at a specific composition. So let me tell you why they are called as minimum boiling azeotrope when they show a large positive deviation. Again, they have given example for large positive deviation, that is minimum boiling azeotrope. Here example is ethanol water mixture obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition and no further separation occurs. Now when this 95% by volume of ethanol is formed, this becomes an azeotrope. Now this 95% by volume of ethanol, that solution is nothing but an azeotrope. So now this will have the liquid and vapor phase to be same composition, that is, this liquid and vapor phase of the ethanol will be having same composition and further separation cannot be possible with the help of fractional distillation. The solutions that show large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Now example for Maximum boiling azeotrope is that nitric acid and water. It's an example of this class of azeotrope. This azeotrope has the approximate composition 68% nitric acid and 32% water by mass, with a boiling point of 393.5 Kelvin. Now I have got this table here, so I wanted to explain why it is called minimum boiling azeotrope, and it has got positive deviation, right? When it has got positive deviation, see why it is minimum boiling azeotrope, because now we saw the example of ethanol and water for minimum boiling azeotrope, right? So ethanol's boiling point when it is a pure substance would be 78.3 degrees Celsius. Boiling point of water would be 100 degrees Celsius. Now when they form a solution, AB will be the solution. So this will become an azeotrope, and that azeotrope will carry the boiling point of 78.2, which is that the pure substances had two different boiling points, and the solution that was formed carried the minimum boiling point of that two substances. That is like, you understand, right? See, these two are the boiling points of the components that are going to make the solution. Now here the boiling point of ethanol is lesser and boiling point of water is greater. So when the solution formed has got lesser boiling point, then it is called as minimum boiling azeotrope. That is, the azeotrope formed has carried the minimum boiling point of the two components from which it was made, right? Here again, let me tell you, ethanol and water are the components which are going to make the azeotrope, and when the azeotrope is formed, when the solution is formed, it has got the boiling point of the minimum, it has got the boiling point of ethanol, which carries the minimum boiling point of the two. Between ethanol and water, ethanol has got the minimum boiling point, and azeotrope is also getting the boiling point similar to ethanol. That means it is the minimum boiling azeotrope. Talking about maximum boiling azeotrope, here they have given the example of nitric acid and water. In our textbook, they have given the example of nitric acid and water. Now, looking at the boiling point of nitric acid, it is 86.0. Water is 100. Now, the azeotrope which is formed has got 121. That is, it has got a maximum boiling point near to 100. 121 is basically similar to 100, so it has got the maximum boiling point. It did not get 86.0 or anything near 86. It has got 121, which is maximum boiling point than the two components present in the azeotrope. That is why it is called as maximum boiling azeotrope. With this, we have come to the end of this video. Thank you for watching. If you found this video helpful, please like and subscribe for more educational content. Don't forget to hit the notification bell so you never miss an update. Your support helps us create more valuable resources for learners like you. Keep exploring and stay curious. Bye.